Hi friends, thanks for checking out this video where we're going to be covering AP Chemistry topic 1.2. In this video, I'm going to show you two specific types of calculations that are involved in determining atomic mass. The first one is a bit easier, the second one more challenging, but we're going to make them both as clear and direct as possible for you. Thanks for checking out the video, and please subscribe to the channel if this kind of content interests you because there's a lot more to come. Thanks, and let's get started. Let's do a quick bit of review to set the stage for this video. Firstly, when we look up the atomic mass of an element on the periodic table, for example, hydrogen, we always find it to be a decimal. Now, this is because atomic masses are what we call weighted averages. Now, a typical average is one where you take 2, 3, 4, as many objects as you can imagine, you add all of their weights together, and you divide by the number of objects. But a weighted average is different. In a weighted average, what chemists do is consider how often is a particular isotope found in nature. And if one isotope is found more often than another, its weight affects the average more. A perfect analogy for this is the way most grade books work in high school and college classes. For example, your exams may be weighted more heavily than participation, homework assignments, or lab work. And therefore, scoring higher on an exam can move the average of your grade in a more significant way. So again, for isotopes of atoms, if an isotope occurs more frequently in nature, it will have a bigger impact on the average, and that's why we call it a weighted average. So in these problems we're about to tackle, we're not only going to know the masses of the different isotopes, the different types of hydrogen atoms or carbon atoms, but we're also going to know something about how frequently they're found. We call that their percent abundance. Okay, let's dive into our first calculation using hydrogen. Okay, so here's our first example of an atomic mass calculation. Let's think about hydrogen. When we look it up on the periodic table, we see that its atomic mass is a little bit over 1. Where does that number come from? Well, in questions like the one I'm about to show you, you're going to be asked to calculate the numbers that are found on the periodic table. How is it done? It turns out that hydrogen has two isotopes. In other words, hydrogen tends to come in two different varieties, and they just differ in the number of neutrons. Now, the first variety is known as protium. It has a mass of about 1.0078 AMUs, and it is occurring almost all the time when we look at hydrogen atoms. 99.989% of the hydrogen atoms in the universe are this particular isotope. But there's a second isotope, less common. It's called deuterium. Its mass is a bit more. It has an extra neutron. Its mass is 2.0141 AMUs. But again, it's very rare, and its percent abundance is only 0.011%. So to clarify, when we see percent abundance, that's the same as talking about how often the atom occurs. So in other words, imagine you have 100 of these hydrogen atoms. More than 99 of them would be one particular isotope, and you have a less than 1% chance of finding one of these deuteriums. Okay, so how do we use that information to find the atomic mass on the periodic table? Well, we're going to treat the two isotopes separately. We're going to look at our protium first. We're going to take its atomic mass, which was given to us, and we're going to multiply it by its percent abundance. But notice the difference. In the problem, it was written as a percentage. But in my equation that I'm using in this calculation, I've moved the decimal place 2 spots to the left. Every time you do an atomic mass calculation of this variety, you must remember to take the percentage given to you and convert it into a pure decimal, which will always be done by moving the decimal 2 spots to the left. Now we multiply that atomic mass by our decimal, and we get this value. Okay, now we go to the other isotope. We take the mass given to us in the problem, multiply it by the percent abundance, but again, it must be converted into a decimal by moving that decimal place 2 spots to the left. And we get another number. Now, we take these two numbers and add them together. And when we do so, we get the number, the mass that's found on the periodic table, 1.0079 AMUs. So in summary, For this sort of straightforward atomic mass calculation, you may have 2 isotopes, as is the case with hydrogen. You could have 4 or 5 isotopes. The problem is always done in the same way. For each isotope, take its mass, multiply it by the percent abundance, convert it into a decimal, and get that particular answer. Do that same thing for every isotope, no matter how many there are, and take the sum of all those calculations that you did, and all together, that will be the atomic mass of that particular element. Okay, I want you to try one similar to this on your own. Okay, here's your opportunity to practice this skill. In this problem, we're looking at carbon, another very common element. Carbon also has 2 main isotopes. We're told that one of the isotopes is noted as carbon-12, and it has a mass of about 12 AMUs and occurs in great abundance 98.90% of the time. The other isotope is less common. It's a little bit heavier. It's known as carbon-13 and has a mass of 13.00335 AMUs. This type of carbon atom is only found 1.10% of the time. Now again, we want to find what the atomic mass is for the element carbon. Remember, we already know what the answer should be because it's given to us on the periodic table, 12.01 AMUs. But of course, when you're asked a question like this, we want to see that you can do the calculations yourself. So a lot of times, you wouldn't just be asked to show the answer, but your work and calculations as well in order to get credit. Now, how are you going to do this problem? Well, similarly, you're going to need to take the masses of the 2 isotopes, as we saw with the hydrogen example. But what are you going to need to multiply each of those masses by? And then finally, when you get those answers, what do you do with them to get 12.01 AMUs? One thing I'd like to point out, in the case of hydrogen, the isotopes had names, protium and deuterium. But you should know that for most elements, there aren't specific names like that. It's actually much more common to just see the isotope noted with the element's name, a dash, and the mass number written after it. So the 12 is the number of protons and neutrons in the nucleus of that type of carbon, and the same goes for the 13 written after the carbon-13. Okay, give this problem a try. When you come back, we'll look at the full solution. Okay, here we are with the full solution to this problem. We take the masses that were given to us in the exam question, and we multiply each of them by the percentage that represents how frequently this isotope occurs. We make sure to take the percentages given to us in the problem and convert them to decimals by moving the decimal place 2 spots to the left. In doing so, we carry out this multiplication, we get our 2 contributions to the mass, and we have to add those together, which gives us 12.01 AMUs. And remember, we can always check that this is the correct atomic mass for a particular element by looking at the periodic table. Okay, now I'm going to walk you through a slightly more challenging version of an atomic mass calculation. Now, in my experience, because the AP exam is a higher level form of chemistry than a typical high school chemistry class, you're much more likely to see a problem like this on the AP exam than the previous examples that I showed you. Let's read over the problem and see how this differs. We're again dealing with an element that has 2 isotopes, in this case gallium. We're told that one of the isotopes is gallium-69. It has a mass of 68.926 AMUs and occurs more than half of the time at a percentage of 60.108%. There's another isotope of gallium. It's gallium-71. But we aren't told anything else about this isotope. We don't know its mass, and apparently we don't know its percent abundance either, although I'm going to show you how we can figure that out quite easily. Notice that this question wants you to find the mass of a specific isotope. You see, the previous problem, we were looking for the overall atomic mass, the weighted average of a particular element. This problem is different. We just want to know the mass of one isotope. So I'm going to show you how to figure this out. Now, I'm setting up the general problem in the same way that I did the previous 2. In other words, I have the mass of my first isotope multiplied by its percent abundance, converted to a decimal, and that equals 41.430. But for the second isotope, they want me to find the mass. They don't give me the percent abundance. So how am I even going to find out this contribution? In other words, there's a lot of missing stuff here. Here's the golden ticket. You already know the overall mass for this element because you can use your periodic table. When you look up gallium, you will find, depending on the periodic table you look at, they differ in their atomic masses a little bit, that the overall weighted average is about 69.723 AMUs for this element gallium. That's critical. Don't forget that you can use your periodic table. Now I'm going to show you how we can use this and the percent abundance to find some missing information so that there's only one thing we have to figure out. Because as it stands now, it looks like we're missing 3 critical pieces of info. Okay, first, we know that this weighted average is the sum of this number added to whatever this number is. So all we have to do is use subtraction. This missing number is 41.430 subtracted from 69.723. When we do that simple math, we find that this missing piece is 28.293. Okay, so we're slowly going to fill in these missing puzzle pieces. Next, let's look at the percent abundance. We know that the first isotope occurs about 60% of the time. Remember, there's only 2 isotopes. So in total, what do their percent abundances have to equal? That's right, 100%. So we're going to use subtraction again. If I know that this number plus this number, when in percentage form, need to equal 100%, let's just subtract 60.108 from 100, and we'll find that other missing percent abundance. It turns out that that percent abundance is 39.892. That's 39.892%. Now, we need to convert that into a decimal if we're going to use it in this particular setup. So 38.892% is 0.38892. Okay, so we found out these 2 pieces just by using some reasoning, by using subtraction, by using information that was already given to us. Now we're going to answer the question. How are we going to do that? How are we going to find what this mass is, the mass of gallium-71? Well, if we just look at this line here, we have a very standard algebraic equation. We have an unknown, so let's call that x, and it's being multiplied by 0.38892, and it equals 28.293. So we're just going to solve for x. How do we do that? Well, we're going to move the 0.38892 to the other side using division. So I'm going to divide this side by 0.38892. And then also divide this side by 0.38892. Right? So all you have now is, let's get rid of this piece. We have x, which remember is our unknown, is equal to 28.293 divided by 0.38892. Okay, so what do we get when we put that into our calculator? The missing mass for gallium-71 is 70.925. That's the answer to this question. Now, of course, you can always check your work. Now that you have the mass and you have the percentage, you could put these numbers back into your calculator and see if they do, in fact, equal 69.723, which is the mass confirmed by the periodic table. Okay, so this is a little tricky one. Make sure that you remember the steps involved, which is finding the missing percentage, just using subtraction, find the missing contribution to the overall mass, again, using subtraction, and then just setting up an algebraic expression to solve for that missing piece. Thanks. Thank you for watching this video, everybody. You're one step closer to mastering the content of section 1.2. I'll be making another video shortly about mass spectrometers and how that ties into this concept. And I hope this was helpful for you, and I hope you have a great day. I'll see you in the next video.